Hello, and welcome to another lecture. As we're looking at the argument principle, which is subsection 5.4.1 in the book, and you can get the book from the link in the description. All right, so first, let's start with some terminology, just in case it's not clear. So if we say zeros or poles counted with multiplicity, that means that whenever we have a zero or a pole with higher order, we count it with that order, with that multiplicity, right? So for example, if we have z squared times z minus 1 cubed, right, that has the zeros at 0 and 1, but it really has 2 zeros at 0 and it has 3 zeros at 1, right? So it really has 5 zeros. 0, 0, 1, 1, 1, right? Those are the zeros of this function counted with multiplicity, right? So that's what we mean. So now we have the argument principle. So suppose that we have an open set U in the complex plane, and we have a cycle gamma in U that is homologous to 0, right? And again, what we mean by that, if you recall, is that it doesn't wind around anything in the complement of U, right? So, for example, for simply connected U, every gamma is homologous to 0. All right, so suppose that we have an F in U, and we're assuming just meromorphic, not necessarily holomorphic, meromorphic. So we're allowing poles, right? So zeros and poles. So it's a function with isolated singularities in U, which are poles, right? It doesn't have to have any poles, of course, right? And the poles or zeros are not supposed to be on gamma. So none of them are on gamma, right? So gamma goes, somewhere else. It doesn't go through the poles, right? So if it goes through the poles, move gamma a little bit, right? Now suppose that z1 through zn are the zeros of f counted with multiplicity. So suppose that we have just finitely many zeros in U, and P1 through PL, again, finitely many, but let's suppose that those are the poles of F, and these are both counted with multiplicity, so just like over here, right? And then what the argument principle says, or the simple version of it is that this integral, the integral, really, well, 1 over 2 pi I, who cares, it's just a constant, but the integral around gamma of f prime over f, right, which is, derivative of log f, right? So that's what's up here. That guy is, we sum, first we go over all the zeros, so the z sub k's, right? And we sum all the winding numbers of gamma around those zk's. So if it doesn't wind around those zk's, they don't really matter, right? And if it winds twice, you put a 2 here. And in the simple case, when gamma just winds once around the zk's, right, you're just counting those zeros, right? And then we subtract the same thing for poles, right? So we sum over the winding numbers for the poles. So again, if it winds around once, you're just adding the number of zeros that gamma winds around and subtracting the number of poles. Right? Now, there is a slightly more complicated and actually quite useful version of the argument principle. That's if you stick in a holomorphic function. So you take any holomorphic function in U, any holomorphic function, and you put it inside the integral. You integrate it against the f prime over f. Right? Then what you get is that h is evaluated at the zeros and at the poles, right? When you're counting them. So you just, sorry. I felt a sneeze coming on. Then it didn't come. All right, so you're basically just evaluating the function h at the zeros and at the poles of f, right? So that can be actually, we'll see later on that can be quite useful. All right. Now, just a small remark. I mean, we did say finitely many here. Really, a priori, you could have countably many. I mean, there are discrete points, so there's going to be countably many zeros or poles. But the thing is that gamma, since it's homologous to zero, so it doesn't wind around anything outside of U, it's not going to wind around anything near the boundary, right? And so you could really do this with a slightly smaller U, right? And you can always make U slightly smaller so that F has finitely many zeros and finitely many poles, right? Still for the same gamma, right? So, it's a little bit of a technicality to prove, but you can always assume just that the number of zeros and number of poles is finite when you're applying this, right? But it's a little bit of a technicality. You have to sometimes handle it. All right. Or you could, another way is that you could state it in a different way. You could state it only for those zeros and poles around which the winding number is non-zero, right? But that would make the statement of the theorem more complicated. We didn't want to do that. All right. So let's say a little bit more. So in a lot of the applications, the way you a lot of times you pick the gamma. You get to pick the gamma. So it doesn't really make sense to make it wind around a whole bunch of times around some points. So a lot of times what you do is you make it so that the winding number around various points in U is either 0 or 1. Right? You don't wind around anything more than once. If you get to pick the gamma, you could always do that. And so then what you can do is you can think of the points that gamma winds around once, right? It either winds around the point or it doesn't wind around the point. So the points that it winds around, well, we're thinking of that as the inside of gamma, right? I mean, and the idea is clear. Like if gamma is a circle, right, then the inside of the circle, that's the inside of gamma. That's the points that you wind around, and then everything outside the circle, well, you don't wind around. So that's not the inside of gamma, right? Now, if there are n zeros and L poles for this for some f inside this gamma, so where the winding number is 1, well then the argument principle is just this, right? And so for example, if the function is not meromorphic, if it's holomorphic, then L is 0 and you just get the n, right? So then it just counts the number of zeros, right? All right. Now, really, why is it called the argument principle? Because we don't really see an argument in this in this integral. Well, the thing is to think, what is it, right? I mean, the antiderivative of f prime over f, right, is log of f, right? The holomorphic log of f, right? Which really, by definition, it's not a function, right? It's this multiple valued function, right? I mean, the real part is fine. The real part is just the real log of absolute value, modulus of f, right? And then the imaginary part is the argument. Well, that's the multi-valued part. So as you traverse around gamma, right? The real part, well, gamma is, well, it's a cycle, so it's a bunch of closed curves, right? So maybe it's just one curve. Think of it just one curve, right? You traverse around gamma. By the time you get back to the same point, well, the real part is back where it was, right? So, so the integral doesn't give you anything. But on the imaginary part, the argument grows or goes down, right? Because you have to, when you're going around, right, you're moving the argument a little bit. I mean, we saw this before, right? When you were looking at, we started was integrating 1 over z, right? So, but now you're looking at argument of f, not right, not of just c, right? So, so what you're doing is you're looking at the change of argument as you travel around the gamma. Right? That's why it's called the argument principle. And, well, we divide by the 2 pi I. Well, the I, because of this I, right, in front of the, it's maybe got already too highlighted. The I because of this I, right? And then the 2 pi, well, because we really want to count, how many multiples of 2 pi we got. All right. So, and here's another interpretation of the argument principle. Well, we could also do a substitution, basically, right? Like the calculus substitution here, right? And so this integral, another way to write it is this, right? It is the integral of 1 over some zeta, right? I mean, you basically use the, think of gamma, gamma is one of the curves. So this is just when you have a single curve, not a whole cycle, but a single curve, right? That, well, it's supposed to be a closed curve, right? But a single closed curve, right? And you do this change of variables, then this is what it is, right? So you look at, you're really integrating the 1 over zeta around the curve f composed with gamma, right? So you look at where f takes gamma, and that, it might make it wind around a bunch of times around 0, and you just count the number of times that it winds around 0, right? So this is another interpretation of this integral on the left-hand side. All right. So let's look at the proof. And so what we're going to do is we're going to prove the second. Let me go back maybe. Oops, went back too far. We're going to prove this second version, right? Because if we prove the second version, well, we get the first version just by sticking in h equals 1, right? So if we prove this, we've proved the whole thing. So let's just prove that. Let h be an arbitrary function and holomorphic, and let's prove the second formula. So, all right. So now h times f prime over f has isolated singularities at the zeros and the poles, right? Well, if it is a pole, well, it's a singularity, right? It's not defined there. And when it's 0, well, we're dividing by 0. So yeah, we get isolated singularities at both, right? Zeros and poles, right? So take S to be this set of these zeros and poles, right? Just so that we have some name for it, right? Now, by the residue term, which is really, that sort of proves the whole thing, right? We just have to sort of, interpret the result of the residue term, basically, right? So this integral by the residue theorem is, well, this is what the residue theorem says. You go over these the points in S, you take the winding number around those points, and you take the residue of this guy at those points, right? And you sum that. That's what the residue theorem says, right? So really, we just need to, compute the residues, right? And we so if there was no h, right, what we'd want the residue to be is really the order of the zero or the pole. Or if it's a pole, we want minus the order, but because we really want to, if p is a zero of order m, right, we really wanted to count it m times. So we really wanted to sum over it m times, or in other words, just have it m times the winding number of gamma around that p, right? And then if there's h, we need to, multiply that by the value of h at that point. All right, so consider that we're at a 0, so p is a 0 of multiplicity m, or a pole of order minus m, right? And so that's, what I said just before. I mean, we want this to be h evaluated at p times m, right? Okay. So, so what are we getting? Well, so first, let's suppose that it's the origin, right? Because, well, I mean, this doesn't really make a difference if we shift everything. And if we don't make it the origin, then this is going to make the formulas ugly, right? So, the residue doesn't change if you translate everything, right? So we might as well just translate to the origin, and we just need to do it at one of these, right? One of these points, and so we're assuming it's the origin. And so now write f as z to the m. So that's where this comes in. We can always do that. We can always divide out. Well, if it's a 0 of order m, then we can divide out by z to the m, right, and get something that's non-zero. If it is a pole, then, well, it's supposed to be 1 over z to the m times something that's non-zero, right? So that's precisely what we're getting here, right? Now we write h as, well, the value of h at 0 plus higher order terms, and all the higher order terms are divisible by z, so we're going to write it as z times, let's call it a capital H. I don't have any imagination, right? so higher order terms of h, right, was z pulled out, right? So it's z times something, right? We don't really care what that something is. Well, you'll see that we don't really care. So let's look at what this thing is near 0. Well, we just expand, this thing in terms of these formulas, right? And of course, I have to do, to take the derivative, I have to use the product rule, but yeah, of course, that works, right? So that's just what it is, right? Take the product rule and the top, and then, over here, that's just little f. And now we expand, not maybe completely. So, this h naught, well, if I look at this part of the fraction, I get this, right? Because I'm going to have h naught, and then, the capital F cancels, and z to the m minus 1 over z to the m, well, it's 1 over z, right? And then I get the m out here. All right. So that's the first term. The second term, right? That's this guy times this, right? And then here the z to the m cancels, right? So we get this term, and then the last term, I don't really, expand anything, right? I can look at this. Now the z, right? I move it up here, so this is going to be z to the m, and this is going to be z to the m plus 1, and then I cancel out, right? So, that's where I'm getting this expression out here. So it's h of z times this nonsense out here, right? Now, why did I do all that? Well, the reason why I did all that is now I have, the things in the denominator here, that's f. F at 0 is non-zero, right? So these things are holomorphic near 0, right? Holomorphic at 0, through 0, in the neighborhood of 0, right? So the only thing that's not holomorphic is this guy, right? It's some constant times 1 over z. Well, what is that constant? That's precisely the residue, right? That's by definition what the residue is, right? It is the coefficient of 1 over z, right, in the expansion, in the Lorentz expansion, right? So we've computed the residue, and that's exactly what I said it's supposed to be. It's supposed to be that m, right, times h evaluated at the point, which we're assuming is the origin, right? So h at 0. right? So, all right. So we've proved the argument principle. It really is. I mean, it's once you're here, it's just a little bit of computation. So it's really the residue theorem, right? Interpreted correctly for this function, right? You just compute what that means. You get the argument principle. Right. So let's think about some sort of applications. Maybe this is not what we're interested in right now, but an application of the argument principle that might not be immediately obvious, but it could be used for locating zeros of homomorphic functions or polynomials, right? I mean, zeros of polynomials, that's a very applied thing to do, right? So a lot of people are interested in, I have a polynomial, what are its zeros? And it's hard, right? Unless it's like a quadratic or a cubic or a quartic, where we have formulas, but in general, we don't have formulas. And so, might want to locate the zeros, right? Or, the most famous problem in number theory, right? The Riemann hypothesis is really about locating zeros of a certain function. Well, whatever. Let's not get into that. But you can basically find where the zeros are by approximating this or computing or approximating this integral. And notice that you don't have to compute this precisely. I mean, you could do this numerically because this is an integer, right? So as long as I do it so that I know that I'm within half, right, of the real answer, it's just an integer. I know what it is, right? I mean, if the error is 0.4 and I get 2.3, approximation, I know that the actual value is it's going to be 2, right? So, all right. So that's one application. Now, a related application is that we don't just locate them like, here when we were locating them, we like put a gamma somewhere, right? And say, well, I want to know like which zeros are in here, right? How many zeros really? That's what it's telling me, right? I can just sort of move around maybe a little circle, right, and compute this integral, and it's going to tell me if there are any zeros in that circle, right? But okay, so then I get them just sort of, well, they're within that circle, right? What if I want to know them, right? Well, I could plug in different h's, right? So in general, if I have these n zeros inside gamma, and let's suppose gamma goes around there once, and I plug in z to the k, right, for any k, I get these power sums of the zeros. Now, from the power sums, I can actually compute the zeros, right? Well, that's solving polynomials. It might seem, well, isn't that sort of what we're trying to do? Well, but you might have a polynomial of degree 500, and now I know that maybe like within this gamma, I know that there are 2 zeros, right? And so I just do it. I just compute this integral for with k equals 1 and 2, and I will actually get if I know the z1 plus z2, and I know z1 squared plus z2 squared, I will know both of them by solving the quadratic equation, even though like the original polynomial, this had too large of a degree, right? So once I've sort of split up a little piece, right? Okay, so that could be used, right? Now, if I know it's simple, I don't have to solve anything, right? If it's a simple zero, right, inside gamma, just do it with k equals 1, right? If there's a single zero, let's call it z naught, right? If I compute this integral somehow, well, it gives me precisely, gives me the zero, right? So I just know it's somewhere within here is the zero, and I just and I will somehow compute this, or maybe numerically if I'm only interested in approximately, right? All right, so So those are just some sort of simple application, sort of non-theoretical application. We'll see some theoretical applications later on, but it's of the Argand principle. All right. So next time we're going to look at Rouché's theorem, which another another in the string of these theorems about basically counting zeros. That's what we're looking at. So that's basically Rouché's theorem basically tells you that if you don't change f much, you don't change the zeros, and you can sort of see it here. So if let's suppose I look at this, right? Well, if I haven't changed this much, right? This function, so I haven't changed the thing that I'm integrating, the integrand in this expression. Well, it couldn't have changed z not much, right? So another way of thinking about it, Rouché's theorem says that if I'm inside some gamma, if you haven't changed f much, then inside that gamma it's the same number of zeros, right? Well, you can see that from here, right? So all right, so that's what we're gonna do next time. So see you then.